Welcome everyone. Good morning, good afternoon, uh, good evening, anywhere in the world. So, thank you for joining us for today's FIBERTalk webinar. I'm here, Rusafi Alam from FTTH Council Asia Pacific. I hope everyone is doing fine. So, our webinar topic for today is 5G Fronthaul evolution, fiber and transport test diversification challenges. So in this webinar, we will cover the following topics. The topics will be like 5G fronthaul evolution overview, fiber densification and WDM test best practices, then network traffic quality test with eCPRI, PTPs, SycE, 1 PPS, GPS application coverage, etc. And finally, field test process automation for enhanced effectiveness. So today we have been joined by Celio Terame, who is the regional product line manager at VIAV Solutions. He has over 13 years of experience in telecommunications test and measurement solution consulting at VIAV. He's based in Japan, and his main expertise on fiber optics, transport, and RF technologies. So just for the audience, we have some handouts out there in the handout section. If you go there, you can just download those and have a look at some time. And after the presentation, we will have a Q&A session. If you have any questions or queries at any point of time, you can just type them in the questions panel, and we will try our best to discuss with the speaker. So now, without any further ado, I will hand over to Celio for his presentation. Celio, please welcome.
Thank you, Rosafi. Let me start sharing my screen. I think this is the one. Please let me know when you can start seeing.
Yes, it's in full screen now. Please proceed.
Okay. Thank you, Rosafi, for the introduction. And thank you, everybody, for joining this webinar again. This is, I think, the second series of the webinars that we present here. Last time we had presented more on 5G fiber focus. Today, we are going to talk a little bit more. We are going to extend our content, not only to fiber, but talk a little bit more on the transport side of the network and how these are getting diversified and how these are bringing more challenges to the network operators. And today, we will be talking basically about three topics. One would be the 5G network evolution overview. Then we will touch about the fiber WDM densification part of the 5G fronthaul. And then on the 5G fronthaul transport test difficulties too, on the topics that Rusafi mentioned, like PTP, synchronization, eCPRI, 1 PPS. Today, VIAV offers a complete broad portfolio for the field test solution from the core side up to the RF side. And last time we focused a little bit more on this fiber portion, where we talked about fiber inspection needs, power measurements, and WDM OTDR. And today we are going to be talking on this fiber again, some focus on the WDM side and the transport. And we also offer some more other portfolio that covers the RF part of the network installation. So right after having all the network on the fiber side, front haul, mid haul, back haul installation done, you will also need to do some over-the-air measurements. And this is where we actually are strong as well, together with transport and fiber. But today, we will not be touching on this part. We will be happy in conducting this kind of series in another time, probably. And based on this portfolio, what we'll see here, the 5G evolution that we see today, comparing to the LTE now becoming 5G, it has been a few years already, and some people may already know, but the RF portion of the throughput, which used to be hundreds of megabits per second, is now becoming 1 to 10 gigabits per second. And this is actually driving a lot more traffic and intensification into the backhaul side, the backhaul that used to be 10 gig to 10 gig, 40 gig, 100 gig is now going up to maximum 400 gig, with now 800 gig on the roadmap coming to the market as well, with some early considerations. But I think this transport backhaul side densification is becoming one of the key challenges from the network operators to consume, to address all of the consumption of the bandwidth. And to do so, we also need to work on how efficiently transmit data on the Fronthaul side and use important resources, how to save important resource on fiber. And to do so, some of the eCPRI protocol that we used to work on the Fronthaul, which used to be a synchronized protocol, is now becoming a packet-based network based on Ethernet. So basically having all of this eCPRI, which used to be a sync protocol, encapsulated into Ethernet packets and being transported over 10 gig and 25 gig Ethernet. So we call this what we used to call 2.5 gig eCPRI, 9.8 gig eCPRI is now becoming 25 up to 25 gig in Ethernet eCPRI. And this is what we call the Fronthaul MUX. And this is actually this eCPRI based on packet. And the latency, the more and more stringent demand for lower latencies are also driving businesses to have, instead of this, stands for one-way delay. One-way delay from the core to user, or the user to the core, that upstream or downstream could be 10 milliseconds, now are a little less than 1 millisecond. And those are driving applications such as remote driving or remote surgery, low latency applications. Now, synchronization as well of the network, time synchronization compared to the GPS, that the allowance used to be around 1.5 microseconds or 1,500 nanoseconds, are now jumping to less than 400 nanoseconds. And this is one of the biggest challenges from the operators, to try to get the network synchronized, all the elements synchronized, to avoid synchronization issues through the network. Now, architecture, I think this is the biggest one. That used to be BBU to RRH configuration. Now this BBU has been divided into control unit and distribution unit, decoupled. So instead of having one box here, you would have the control unit and the distribution unit, and those two units could be separated apart from a few kilometers distances and going on. So we will cover on the distances a little bit later, but this would be one of the biggest differences on the network topology. So basically, operators would have a lot of challenges in trying to address the backhaul transport network capacity by Ethernet, and also to optimize the network. We are coming up with some new technologies such as Flex Ethernet or OTN, or even FlexO for Flex OTN. And the backhaul is also synchronized by PTP and synchronous SycE. Now the Fronthaul side, this will be something different. Instead of eCPRI, now we're going to the Ethernet-based eCPRI, and some of the time-sensitive network. So this would be the data protocol combined with time synchronization. So operators will have to do the inbound communication of the Fronthaul, having eCPRI, PTP, and all other protocols all transported together because of the mix on the technologies. Now, if you see here, this is a nice chart to show how different are going to be the key drivers, like the enhanced mobile broadband, ultra reliable low latency communication, and massive machine type communication. Those are the three drivers that we see in many presentations around. But I would like to emphasize here that some of the URLLC, ultra reliable low latency communications, they require very stringent high demand for latency and mobility, but they don't even need too much traffic. Whereas like for eMMB, They would not require that much latency, but they would need a lot more traffic capacity and densification. So depending on the application of the network and the key end user application, we would have different requirements from the network side. And the network operators, they're demanded to supply for all of these needs, which means we cannot focus on only one type of the network, only on traffic, only on latency, but only on density. But people will need to address all of these requirements simultaneously to go and supply and be able to realize the applications that the end users are requiring. So EMMB, URLLC, and MMTC impose diversification requirements in the network. And we can see from the fiber perspective, well, we used to have an LC duplex connector. Now for densifying the fiber, we're now using MPO connectors that carry 12 to 24 or even 32 fibers in one single connector. Now instead of having dark fiber for connecting point to point, we are now making more efficient use of the resource by transmitting via DWDM, PON, and even OTN for TDM applications, time division multiplex. SycE, that used to be a synchronous communications, now becoming an eCPRI packet-based Fronthaul, so even more flexible packet-based solution. But again, whenever this is becoming a synchronous test, becomes a packet-based test, this requires much more strict and rigorous types of communication testing on the field. This is more on the RF, but instead of having 15, 20 megahertz of the bandwidth that we used to use on the RF side, now becoming 100 megahertz up to 400 megahertz and even more in the newest considerations and studies. Massive MIMO and beamforming, this is also another new technology. And also BBU being spliced, divided into CU and DU for offer more flexible and agile network. These all means that the fiber infrastructure that is being carried in the network itself, so are getting and growing exponentially. So 5G will deliver symmetric OTA speeds from 1 gig to 10 gig per second, bits per second, and in a latency less than 1 millisecond. But we have some coverage issues with the millimeter wave and more small cells densification. And to do so, we're also transporting these RF fronthauls based on 10G and 25 gig. Because of the small cell having narrower coverage area compared to LTE and macro cells, we will have 20 to 30% more small cells installed in the network to have the same capacity and to address all of the network consumption, bandwidth consumption from the end user applications. So to do so means that basically we will have 20 to 30% times more fiber links deployed around the world. And this is actually driving a lot more traffic in the backhaul side. Means we will have less and less, we will have a problem of scarce fiber resources, which means we will have to have more upgrades in the fiber and the transport infrastructure to offer the same capacity using one fiber, less fiber, and having increasing the transport rate within that fiber. So we would have more higher fiber capacity per cell site, which is going to upgrade the network throughput. We will have significant larger number of cell sites that have an exponential impact on fiber endpoints. So basically, if you want to address all of these fiber numbers to be deployed around the world, this is going to consume much more fiber and will require dark fiber installation. But dark fiber installation is going to be very expensive. So some of the solutions that we see around the world for the fiber densification in the fronthaul side, instead of having point-to-point direct connections using dark fibers from DU side up to the RU side. We see now technologies such as WDM or even OTN. So this would be WDM, wavelength multiplexer, and this would be time multiplexing. So we have seen two types of multiplexing in the world, and or even the combination of these two. So today we will focus more on this passive WDM and WDM PON side, which will have basically one fiber instead of having one dark fiber here. It is going to be the dark fiber still, but the operators will have the capacity to multiplex tens of channels within this WDM channel here to supply many different RUs at the end side. So basically, you will have just one dark fiber to carry about, but you will have extra elements in this WDM by having WDM MUX and DMUX, and also making sure that all of the signals that you deliver from the WDM side are being transmitted to the other end, and those are being properly connected. And this is going to be having more and more as a field test people challenges in making the turning on the cell sites at the day one without any problems. Difficult because of this BBU being split into DU and CU and DU. Now we could have some portions of the network that was not present before. We used to have backhaul and fronthaul. Now we have backhaul, midhaul, and fronthaul, separating between the fronthaul is between the DU and RU, which will carry eCPRI or even CPRI in some older deployments, or also for supplying LTE ranges together. We would have range of less than 20 kilometers and latency based on, it could be microseconds, it could be nanoseconds as well. Midhaul, which is the link between the CU and DU, will have an interface called F1, but those are commonly not really tested on the field side. This could be more for the lab, but this could be actually more distance up to 80 kilometers and having milliseconds of latency between. And the core will have interfaces like S1 and ES1 with ranges over 200 kilometers or so. This would be the backhaul WDM ring that used to be the traditional WDM. This topology does not really change much, but most of the challenges on the field will come on this fronthaul side because of the WDM densification and the TDM and all of the synchronization issues that I commented in the beginning. Okay, from now on, I would like to start talking about this Fronthaul 5G WDM testing and muxing. Now, WDM densification imposes having one fiber. Like in this example, this middle of the fiber used to be the dark fiber that was provided in LTE for point-to-point connection. Now operators came to the options of having CWDM, which would be channels spaced every 10 nanometers. And also some challenging operators that will have more channels to supply with less fiber because they don't have the fiber to be ready there. They can also have the option to use the 1550 nanometer range that is transmitted in the CWDM and have actually DWDM muxed inside the CWDM channel. So customer would have around 8 channels of DWDM plus 7 channels of CWDM, meaning 15 WDM connections from end to end, from the CU side, from the DU side up to the RU side. So this would be 1/15 of the capacity, efficiency that we would see in the compared to LTE by using this kind of a complex topology. Now, how to test this kind of topologies? This is a very challenging topology to test, but in case of WDM testing, we would have many portions of test, and normally we used to have OTDR testing only in this part here, which used to be 1310 or 1550 nanometers for dark fiber characterization. But now, because of the CWDM and DWDM MUX DMUX equipment, they will cut off all the wavelengths that are not in this range. For example, 1470, 1490. This CWDM MUX equipment will cut every signal that you will have outside of this range. So if you're testing with 1310 or 1550, you will not be able to pass through this CWDM equipment, and the same happens also in the DWDM. So the only wavelength that you would probably be able to test would be this 1550 around, but you cannot make sure on which exact wavelength you're testing here, because the OTDR would probably be something more broader wavelength coming up. So we have some test equipment solutions to come up with to try to solve this solution. In the previous webinar, I have actually shown this XWDM OTDR, which is an OTDR with tunable laser capability that can go, if you select the CWDM OTDR, or if you select DWDM OTDR, you will have the capacity to tune the wavelength that you want to test, so that you can go exactly on that channel that you want to test to verify end to end. So if you are in CWDM, you can test from up here. You can measure the MUX drop. You can actually measure the DMUX drop and make sure that the fiber is arriving at the other side. The wavelength is arriving at the other side at the wavelength you select in the OTDR. With this, you can conduct a normal OTDR testing focused on that wavelength and make sure on end-to-end connectivity here. But now, some operators, they will have some more challenges, because right after verifying the fiber media, the media itself could be okay. But after this, the operator will have to install the DU at this side and install the RU at the other side, and make sure that both are making connectivity and talking to each other without problems. And to do so, we have different ways of doing this, but the newest solution that we have came up with is this Nano OSA, which is a small optical spectrum analyzer module that we have just released. So with this, introducing Nano OSA. Nano OSA is a module type of optical spectrum analyzer that covers the full band of 20, 60 nanometers up to 16 to 50 nanometers. So it can be used for CWDM, could be used for DWDM, could be used for any other type of communication that uses single mode fiber. So any type of WDM in single mode fiber could be covered here, and we can measure signals down to 37.5 gigahertz channel spacing. We have come up with two options. The full option, which would be an optical spectrum analyzer, would be the OSA 41000. But we have options to also limit all of the capability to, instead of having an OSNR and OSA full measurement, we can limit so that the user can do a quick channel checking on the power and wavelength, just to verify that every signals that you're expecting to have, for example, in this DWDM portion here, you are having here. But the OSA is something that we are recommending to customers so that people can actually see the wavelength, the shift, the shape of the wavelength, and so that makes sure on the signal strength, the tilts, and all the problems that could happen in the network, especially after muxing the CWDM or the DWDM, and making sure at the other end. Now we have a unique feature on this Nano OSA that would be an integrated SFP bay. This is here at the left side of the box. This could be an optical, this is an SFP port that you can plug tunable SFPs. So tunable SFPs available in the market, or also available from Viavi. They can select the wavelength itself. The same way we do with the OTDRs, the tunable SFP can shift the wavelengths to tune to the exact DWDM or CWDM channel and start emitting light here. So with this, you could use at one side a nano OSA with a tunable SFP so that you can go for every channel and make sure that you use this as a tunable light source. And at the other end of the network, you could use another nano OSA, but without using tunable SFP side, you could only use the OSA port so that you're measuring exactly the wavelength that you're transmitting from the other side. This could be very useful for new channel activation. If you don't have a DWDM OTDR, but you want to just make sure that instead of, if you want to add a new channel into the WDM, if you want to make sure on the end-to-end connectivity and the end-to-end power loss, insertion loss, this could be very useful for adding new channels and making verifications without interrupting the current signals, the live signals. This module is available for all the platforms that we supply from Viavi, like MTS 2000, ONA MTS 4000, MTS 5800, Cell Advisor 5G, this One Advisor 800. Those two are actually RF related products that can do RF and fiber testing together, and ONA 1000 for 400 gig testing. This is actually how the user interface looks like. This is a very simple one button press so that the nano OSA itself will do all the calculations inside. It will just tune to your wavelength. It will identify channels. It will guide you to the grid on the ITU-T that you're supposed to do, be transmitting. It will show you the ITU-T channel that you're on. It could show you the offset between the ITU-T channel and the grid that you're actually verifying. If you're receiving a signal that is slightly offset from the ITU-T grid, it could be a signal, and this could be showing on the GUI automatically. Now, how you can use this, it could be having the nano OSA at the beginning of the network, inputting a signal, and measuring at the other side so that you can see all the channels at the inside. If you're having a problem here, you could also go upwards network so that you can measure on the CWDM side here if you're receiving all of the signals, if you're receiving all of the signals from the output port here, or if you're actually receiving all of the signals from the beginning of the point. So this could be very flexible. You can go to any portion of the network to verify the DWDM mux, to verify the CWDM mux, to verify everything mux together. Or if you want to filter on specific channel, you want to just measure all DWDM channels that are coming here. This could be used for any location. And this is a one button simple press that user does not really need so much training. This is a one button press procedure, so very easy for segmenting the network problems. Or you could also use the product for inserting tunable laser sources here and verifying with OSA at the other side so that you can verify insertion loss on the end-to-end link and make sure that your path is okay. This could be also combined with the other traditional DWDM OTDRs that we have shown in the past. So DWDM OTDR can work as a light source as well, but it could also see it could verify every single details on the network to find reflections, to find bendings, and find any impairments in the signal in the network. Okay. So we have talked about the fiber part up to this point. From now on, I would like to talk a little bit on the 5G fronthaul transport diversification. So diversification means that I think everybody knows, but nobody is going to start 5G from nowhere without and discontinuing the 4G. So operators, they must run 4G and 5G in parallel, 3G sometimes as well, 3G in some cases. But for some time, for a few years, operators will have to coexist with the 4G and 5G. So operators will need to, for the backhaul side, for the 4G, where they have a backhaul and fronthaul, and those are separated between the BBU and RRH. Now in the 5G, They're going to do some of the diversification of the network because of the BBU is separated here into CU, DU, and RU by having backhaul, mid-haul, and front-haul. Now for measuring mid-haul and backhaul, those would be pretty similar to what we used to have in backhaul in 4G. So operators, these would be normally based on Ethernet. So they would need to measure bandwidth, measure delay, measure jitter, and packet loss. Jitter here means packet jitter to verify time variation between the packets. And to do so, we have easy test process of automation that is called RFC2544 or Y.1564 that I think most of the people are commonly already know if they are running this type of testing. The only difference would be the rates that used to be 10 gig to 40 gig, 100 gig in the past. These could be 400 gig, 100 gig, or some of the FlexE testing. So all of this RFC and Y.1564 testing doesn't really change much, but the transmission rate goes up pretty considerably. Now for the Fronthaul side, we have more challenges because this will have impose for the network operators to have to measure latency to ensure that this is within the budget here. And also, not only measuring the latency, but operators, they need to make sure on the timing and synchronization together with eCPRI transmission. So here, there will be many types of protocols coming up. It would be eCPRI, it would be timing, and timing is a very broad category that will encompass on starting from GPS testing up to synchronization and verifying every point on the network so that you're going to have not problems on the sync. Now, to do so, to have a link on 4G and 5G separate is very expensive again. So some operators and network equipment manufacturers have came up with solutions that could have a hybrid solution for having LTE and 5G. So in this case, they would have some boxes in the middle. In these portions of the network, they will most commonly have the CU and DU aggregated together so that they are making something similar to LTE, where they would have just one box here inside built in. And here they would have the Fronthaul and MUX for the LTE and the 5G. So for 5G, they would have the eCPRI with PTP. For LTE, they would have the eCPRI or OBSI in some countries. OBSI is something very similar to CPRI, but limited to some countries only. And network synchronization part is, I think, the most difficult side in this network. So, but I think people refer to this as PTP. The most common measurement parameter that is important in every standards that we go to is the time error measurement. This could be measured in various points of the network, it can be separated into constant and dynamic time error, which is shown as CTE and DTE. And these DTE also have the mean time interval error and time deviation testing imposed together. Some operators and standards, they focus more on the maximum time error max. So the maximum time error absolute will be a combination of CTE and DTE in absolute value without showing plus minus. This would be the absolute value. And some operators has chosen to go after this, but in 5G, there are many other parameters that actually need to be tested, and those are set by ITU-T in some of the standards like G.82XX. So we will not cover the standards in detail here. This would require a few hours for going after and explaining in separate. But the operators, they have the options to select which type of the ITU-T profile they want to run in their network. If this is going to be an L2 network, if this is going to be an L4 network, or if they are going to have a unicast, a multicast, these are all set up in the profiles. So this would be easier. Instead of having standards for every single operators, the ITU-T standards actually make this simpler for the network equipment manufacturers and the operators, and also system integrators and contractors that work together, so that they can make sure on the network limits and thresholds for the testing. Now, basically, verify connectivity to the grandmaster clock. This is a must parameter for every type of topology in the PTP network. Now, for this, we have a market-leading solution for that is called MTS 5800 series. I think we are the #1 share on this PTP application for the field in LTE advanced times, especially in Northeast Asia, Europe, North America regions, that people will require some portable operation equipment with very high accurate clock testing, high accuracy clock, so that people can bring this box to the field and strategic points of the network to make sure that the PTP is running together properly within the limits, and together with testing some of the Ethernet, eCPRI, and other protocols that makes all of this testing different but simpler using this MTS 5800 series platform. Just as a brief overview, this is how the product looks like. This has a flexible UE with dual port capability. So every application that you can select here, it will have dual port capability. And for this product in particular, it can support protocols up to maximum 100 giga, just like the name of the product. For Ethernet applications from 10 megabits per second up to 100 gigabits per second, you could have RST2544, Y.1564, and some of the OTN testing up to OTU4 rate into the backhaul. But at the same time, if a customer also needs to do 25 gig Ethernet, SycE, eCPRI testing on the Fronthaul, if they want to do PTP applications, if they want to do some fiber testing as well. So we can supply all of this by having an external backpack module that will have a timing extension module. I will go after this explanation a little bit later, or even the OSA module. This OSA module is something that I showed in the past. So this nano OSA that I presented earlier, this can be plugged in the back of this MTS 5800, so it can run 2 ports on testing, eCPRI or PTP or anything, 2 ports simultaneously, plus an OSA testing, or an OTDR if you have an OTDR module as well. Now for the backhaul, that's okay. For the timing, if again, for testing all of this time synchronization applications encompassing GNSS or GPS, one-way delay, and sync applications like PTP, synchronous Ethernet, Wonder analysis, and 1PPS testing, this is the only one solution, all-in-one solution in the market that can do all together. Now, the core of this time and synchronization testing on the field is not really in this part of the portion, the testing, but this is within the oscillator and the GPS receiver that comes with the instrument. So the module that attached at the back of the MTS 5800, we now have released a new module that is specially made for 5G applications and new testing requirements. So this C5TAM-R2, the revision 2, Rubidium. This is the timing module version 2 that we call. So we used to have a version 1 here. Now we have the version 2. Those 2 are still live and can be ordered anytime. But the common function will be that both of them has a rubidium, a very accurate rubidium atomic clock inside, so that you can make sure on the time accuracy and frequency accuracies that you're testing versus the network. has a capability for verifying the coax cable delay, has 1 PPS Wonder measurement analysis capability. It supports 1 gig, 10 gig, 25 gig PTP applications and can help the MTS5800 to emulate master and slave operation mode into the PTP protocol, and also have some time and phase and frequency profile support for testing all of these ITU-T profiles. It has SycE support, and it also supports Wonder analysis. Now, what is different with this version 2 is that GPS satellites, GNSS satellites, they now have multi-band sensing. So for improving the accuracy, it will show you dual band measurement on every satellite that you receive so that you could have improved accuracy. You could have an RJ45 port for a 1 PPS measurement and also time of day or TOD referencing. And we have a pretty nice accuracy level of plus minus 5 nanoseconds compared to the GPS for measuring the network. So this is very, very important for having all of the parameters set here. Now, how this could help and to be objective and try to see which are the real parameters that matter to the field side. You could have any type of network, but the beginning of the synchronization, we always start with this antenna, the GNSS GPS antenna, and verifying the antenna system that you're receiving is the first step for getting the accurate testing overall the network, because if you're getting poor antenna satellite signals, the whole network is going to be messed up. So with this, we have the capability for the GPS cabling and the antenna, the coax cable that goes into the device with clock. That could be the master or could be the RU, could be anything. So the coax part of the network, you can plug to the MTS5800 and you will get a clear vision on the sky plot so that you can see from the position that you are in the middle of the screen. You can see now north, south, east, west, and you can see the degrees here for 0 degrees, 30 degrees, and 60-degree circles, and see the map of the sky to verify which are the GPS connections that your satellites that are visible. And it also has a very unique feature of nulling multipath signals, so that because if you're having a very poor signal but that is reflected by somewhere like a tall building in urban canyon environment, you will have very poor signal and it contains some latency. It has some ghost signals. So the equipment will be able to identify those ghost signals and make sure that you take out the satellite signals that are containing multipath, so that you can have a better calculation on the timing and accuracy. So this is actually important to verify the satellites and to make sure that you have 4 satellites all the time, at least 4 satellites all the time, 24/7. And that in the ideal environments that you have over 40 dB carrier to noise ratio for every satellite that you receive. But for some urban canyon environments, it could be around at 35 dB, but recommendation would be to have over 40 dB on the CN. And also have a mean 3D accuracy that would be less than 5 meters, because every meter inaccuracy that you have in the position that you are, you will have around 3.3 nanoseconds inaccuracy. And those inaccuracies are going to be carried over the network throughout. So if you have, for example, 100 meters inaccuracy on the position, you'll probably have 330 nanoseconds inaccuracy in the overall network. So that's a pretty much big impact overall. Now, after the cabling and the antenna is measured, another portion of the network that is sometimes forgotten by the operators, and we have been helping some of these operators to troubleshoot, is the cable delay offset. Because the satellite receives a signal, but it has some delays in transmitting the signal up to the grandmaster. And some operators, they know how to do the exact calculation here, but the cabling distance or the inline amplifiers or any surge protection equipment could add some delays here. And making sure on the exact length and the delay that is caused here is also important, because every differences that you have here, this is also being carried throughout the whole network again. So MTS 5800, we have a solution for having, we have a good, very known antenna that we ship together with the product. So this could be the calibration and reference. And based on that, we take the reference, we measure the delay, and whenever connected to the customer's cable or the cable under test, we verify the differences, and it automatically calculates how much the offset the user must input into the settings of the Grandmaster in the beginning. So this Grandmaster offset setting, which is often forgotten to be set up, is going to be very important in 5G, so that every nanosecond of accuracy is going to be important. You want to make sure that it was properly set with the right delay calculation. If you go, after verifying the antenna testing and the cable delay, you will need to go finally to the PTP testing. And normally this is how the old PTP network looks like. We're having a Grandmaster clock, a boundary clock cascaded, some transparent clocks inside, and going into the E node B in the LTE times. But now we have seen, like in specifying the ORAN, we're having ODU, which will have the Grandmaster capability together. We'll have a BC inside the network, and the RU will have work as a slave in the network. So here we have ways for testing the Grandmaster network time synchronization quality by plugging the MTS 5800 right after the Grandmaster. We have ways for receiving testing the overall end-to-end time error compared to GPS by connecting to the boundary clock closest to the RU and verifying how many nanoseconds is this offset from the GPS, so that you can calculate the absolute time error and make all of the other parameters. Now for some of the G8275.1 C-run hub aggregation, this is in the standards too. This would be some of the network topology where you have the antenna, you have the master clock, you have the network routers and switches, you would have the FTM muxing equipment, and going to the 5G equipment, or you could have SycE going to the 5G equipment. You could have eCPRI here where you have DU only, or DU and CU all together, working as a boundary clock and transmitting signal to the other side of the network at the RU side. So most important measurements that you would probably do here would have max time error, absolute max time error measurement, constant time error measurement that is normally calculated after 1,000 seconds of running time of the test, or sync packet delay variation. Those would be the three most important parameters that you would need to test. And in the network, you would test here at the router interfaces, at some of the WDM ports, on some fiber demarcation points that you will probably receive the dark fiber from the operator, or even, and also testing here at the master clock. If you go at the tower side here, you will probably need to test at the WDM port. So this is actually linking to the beginning of this webinar where you need to test the WDM part and also the fiber demarcation. So this is important that you go and test PTP at every portion of the network. Okay, so we are running out of time a little bit. So if anybody is a little bit more interested in PTP and time synchronization, we could come here and have separate sessions individually. So please let us know. At the last portion of a few minutes more to go, we would have this SycE and eCPRI transmitting together. But for the eCPRI, we have a different type of measurement solution. And in the standards, this is actually specified that inside eCPRI, you could have different message types that are transmitted. So if you have a WDM, a DU, and RU, and if you have a Fronthaul transport node in between that you have WDM or even TDM testing, muxing, you can set the equipment to transmit IQ data, for example, for payload. You can set equipment to transmit every other seaplane type of messages, and verify at the other end that you're receiving the same number of packets and you're receiving the proper throughput, and also conduct a one-way delay measurement. At the same way we can do here in the eCPRI. Inside eCPRI, there's a message type that specifies one-way delay. So for having a GPS here, you will have a timestamp of the on the packet. You will transmit through the network, and the other hand side, you will see the timestamp and compare versus the GPS, so that you can verify the one-way delay from DU to RU and from the RU to the DU side, so you can make sure that one-way delay is within the limits over time. So I think this is pretty much for all of the testing that we have shown today. We support a remote access capability via cloud. This is not internet, but this is internet. So in the cloud, if you have a field technician in the field that is having some problems, that you need some help to support these guys, you could have a free app that we have in our website. This could be for iOS, Android, Windows. In the cloud, we have a server that will provide a one-time access code to the testing instrument. The test instrument guy will help the person at home at office given the access code, and instantly you can start getting remote control. You can transmit data. You can make sure that you send out all of the data through the cloud to your PC without having to attach to emails, or you need to go back to the office to make a USB connection or anything. You can do this remotely, and this is actually very helpful in COVID times. So most of my time today, half time of my week, I support customers and sales and engineers on the field side from my home, actually doing all of these tests. And some of the operators in Japan have started deploying this type of topology for having people bring in the test equipment only and having knowledgeable people, engineers at the office side, so that you can visit more sites per day and you can do more jobs per day. Okay, this is the last slide. So thank you very much. With this, I covered the fiber and the transport side of the field testing inside our overall 5G portfolio. We are proud to have fiber, transport, RF, and all of the testing into the StrataSync cloud testing. So somebody who is more interested in having this type of solutions or trials or demos, please do not hesitate to contact us. And with this, I go to Q&A, but sorry, Rusaki, I think I'm about 5 minutes off. Right?
Not a problem. Okay, so thank you, Celio, for a nice presentation. I think that included lots of insights about your business and about 5G and some other aspects as well. So we will now move to Q&A session. So to the audience, I'd like to request, if you have any queries or questions, please type those in the box in the platform or in the app. Go to questions section and just type in your questions, and we will read out that and discuss with the speaker. So let me see some questions. Okay, so I have started getting some questions. The first question is from Delay. The question is, what frequency bands are able to use for backhauling? Celio.
What frequency bands you mean?
Yeah, frequency bands.
This is very for the backhaul, right? So
Yes,
the backhaul would be probably a wireline section. It would not be an offline. It would not be an OTA. So backhaul, I've seen people running mostly WDM in the C band. C band would be something around 1550, 1500 to 1550 nanometers range. That you would have every channel transporting 100 gigabits per second, 200 gigabits per second, 400, 600. We've seen like equipment like Sienna, Nokia, others transmit in 800 gigabits per second per wavelength. So in Japan, we see L-band usage, but I think most commonly in APAC and in the world, probably they use C-band.
I see. Okay, so the next question is, can it be used with my own tunable SFP for WDM test with Nano OSA?
Yes, if you have a box, for example, with a tunable SFP that supports DWDM testing or CWDM, depends on the tunable laser that you have. You could combine. You could either plug this SFP in the Nano SA, or if you have only one Nano SA and you don't have anything, you could use like a media converter with your tunable SFP at the beginning of the network and use Nano SA at the end of the network so that you can get end-to-end loss. And you could also run a reference measurement before you go and do this field testing. So that's actually a good idea. If you have a tunable SFP, that could be very useful.
That's good. Okay. So the next question is, in environments like that, there is no GPS access or signals inside the buildings or underground. So how can we test PTP time error that time?
That's a nice question. So one of the key advantages we offer with the timing expansion module V2, the TEM V2 on the MTS 1500, is that it has a very high accurate rubidium oscillator inside, so that it can provide you something that people call holdover. So whenever you have a rubidium oscillator that is disciplined versus the GPS, GNSS, you sync the oscillator with the GPS for a long time, for like 12 hours, 24 hours. And then after, you can unplug the GPS signal, and you can the oscillator itself will run in holdover mode. So it will have the TOD, it will have all the frequency references, and you can test this data, the tester, in holdover mode to like underground or inside offices, like you said, and run the measurements in very accurate precision. So it has some limitations on the timing, but you can run this through a few hours of holdover, or even more if you use some other methods that we can teach. But you can, like some Japanese operators, they can run holdover in a specific way, the way that we have taught, for up to 6 to 8 hours. So this is a very unique feature that we can provide, so people don't need to have access, especially like in data centers when they don't have access, or underground, like you said. That's very important to have this holdover capability.
I see. Okay. So the next question is from Venkateswarulu. The question is, what would be the criteria to define ranges in front, mid, and backhaul?
Those were very well studied in 3GPP and also in ORAN. So this is actually in the standards, and we see some operators that actually don't follow these rules, and they can go over, like we see some Japanese operators too that goes double of the distances that are specified. But basically, this is how the standards has been made, so that the equipment vendors and the operators, they will get together so that they want to have all the standards. So this was actually the limits that we came up with the standards.
Okay.
So that everybody could have the same kind of deployment and development.
Okay. So the last question for today I will take is how we are meeting stringent and jitter latency in vRAN, and another part of the question is how we could be different from CRAN.
Could you repeat again, please? Sorry, the jitter part.
How we are meeting more stringent and jitter latency in vRAN. This is one part, and the next part is how it would be different from CRAN.
Okay, actually, how we are meeting those stringent requirements in vRAN, those are probably run in VDU, VCU, virtual environments, right? Where you have in a generic PC or server and testing and having all this BC testing. This is actually very difficult, and I've been helping some operators running vRAN, VCU, VDUs, and everything virtualized. It is really complicated, and some of the networks operators, they are not getting the limits and the quality of performance regards to jitter and timing synchronization, because basically on the hardware limitations of the server. Second would be some of the software limitations by the virtual software equipment vendors as well. But we've seen some of the successful ones, and sincerely, I think those would need to be sacrificed on the class of service that you're running, because if you want to go category A, very nanoseconds accuracy, this could be very difficult to go with vRAN, but for broader and like for EMBB applications, nice traffic, good traffic, but not really much time sensitive, this could be much more than enough. So this could depend on the network topology and what would be the requirements for end user applications. So very, very difficult question, but very interesting.
Okay, so with this we will finish our webinar today, and I'd like to thank all of the audiences who have been enjoyed today's webinar, and special thanks to Celio for hosting the event. And our next webinar information and registration link will be shared with you in due time. And with this, I'd like to thank you all for today. So thank you, everyone. Take care.
Thank you very much.